The calculations for multiple regression. The calculations for multiple linear regression help determine if a group of independent variables, called x's, have a relationship with a quantitative dependent variable called y, and to evaluate how effective the x's are in explaining variance in y. They also allow us to estimate the effect of each x on y and to predict the values of y based on the values of the x's. The multiple regression model assumes that in the population y is a linear function of the x's, called x1, x2, x3, etc., plus an error term. The model states that y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 up to beta k xk plus e, where k is the number of independent variables. The first step in a multiple regression analysis is to calculate the regression coefficients b0, b1, b2, b3, up to bk. These coefficients define a regression equation that most closely resembles the observed sample data. Y hat equals b0 plus b1x1 plus b2x2 plus b3x3 up to bk xk. As with simple regression, these coefficients minimize the total sum of squared error from the observed sample points to the equation. The sample data for multiple regression consists of several observations, each of which contains measurements for the y and all of the x variables. Measurements for each variable are listed down a column. The calculation of the regression coefficients from the sample data is almost exclusively done with Excel or statistical software, usually found under regression or multiple regression, and it is relatively straightforward to obtain the coefficients if the correct columns are specified as y and x's. For example, if we have a dependent variable called y and three independent variables called x1, x2, and x3, then using Excel's data analysis tool, selecting regression, and specifying the appropriate x and y ranges, the regression output is generated and we find the coefficients are b0 equals 3.174, b1 equals minus 0.129, b2 equals 1.478, and b3 equals minus 0.738. We next perform an overall test for significance called the f-test to see if the model has any value. The null hypothesis is that none of the x's have a significant effect on y, which can be written as beta 1 equals beta 2 equals beta 3 equals up to beta k equals 0. This hypothesis is tested with an f-statistic found in the ANOVA table of the regression output. The f-statistic is the ratio of the average amount of variation explained by the model over the average amount of variation that is unexplained. A larger f indicates a stronger model. This can also be thought of as a test to see if the observed r-squared value, representing the percentage of variation explained by the model, is significantly more than 0. The larger the r-squared value, the larger the f, and the more significant the evidence to suggest that the null hypothesis is not true. If the f-statistic is large enough, that is, if the p-value is less than the level of significance, then we reject the null and conclude that at least one of the x's affects y, or in other words, that the r-squared value is significantly larger than 0. This means the overall model is significant. Note that if we do not reject this null, there is no reason to analyze this model any further, since there is no evidence that any of the x chosen has any relationship with y. If we do find the f-statistic is significant, we next want to test which of the x's have a significant effect on y. We do one hypothesis test for each x, and as with simple regression, the null of each test is that the particular population coefficient beta j is equal to 0, which would mean there is no relationship between xj and y. The alternative hypothesis is that beta j is not equal to 0, meaning there is a relationship. This test is necessary because it is possible for there to be no discernible relationship in the population, but it happened by chance that our sample appeared to suggest a relationship. The test statistic for each hypothesis test is a t with n minus k minus 1 degrees of freedom, where n is the sample size and k is the number of independent variables in the model, and each t statistic equals bj minus beta j over sbj, or bj minus 0 over sbj, where sbj is the standard error of the estimate bj. The test statistic basically tells us how many standard deviations the sample coefficient bj is from 0. As in simple regression, the value of each sbj is in the regression output next to its coefficient bj in a column labeled standard error or std period error. Also, the value of each t statistic is shown in the output in a column labeled t or t-stat, followed by the p-value for that test. In our example from Excel, we see that for x1, the test statistic is minus 3.518 with a p-value of 0.072. For x2, the test statistic is 20.294 with a p-value of 0.002. And for x3, the test statistic was minus 7.039 with a p-value of 0.020. As with any other hypothesis test, we reject the null when the p-value is less than the significance level alpha. For example, if we used alpha equals 0.05 for each hypothesis test, for x1 we do not reject the null because the p-value 0.072 is greater than 0.05. For x2 and x3 we do reject the null because the p-values 0.002 and 0.020 are less than 0.05. Thus we conclude x1 does not, but x2 and x3 do affect y. Next, we may wish to evaluate how effective the x's are in explaining variance in y. As with simple regression, we use r squared, which is the percent of variation in y that is explained by all of the x's. Again, values of r squared closer to 1 are better since they indicate the x's do a better job of explaining variance in y. R squared is SSR divided by SST, which are both found in the ANOVA table. However, the value of r squared is usually read directly from the output. In Excel, r squared is under summary statistics. For our example data, r squared equals 0.9990. Generally, r squared over 70 or 80% would indicate a strong model and over 50% would indicate a mediocre one. Often an r squared under 50% would be considered not very accurate. However, the interpretation ultimately depends on the application. For this example, an r squared of 99.9% would indicate a really strong regression model. As with simple regression, we often want to interpret the values of the coefficients b1, b2, b3, etc. Each coefficient bj represents the estimated increase in y as that xj increases by 1 unit. That is, change in y divided by change in x, or rise over run. In our example, b2 equals 1.478, so we would estimate the value of y increases by about 1.478 units when x2 increases by 1 unit. Similarly, b3 equals minus 0.738, so we estimate that y decreases by about 0.738 units as x3 increases by 1 unit. The final type of calculation often done in multiple regression is to predict a value of y based on the given values of the independent variables. In this situation, we simply use the regression equation and substitute the estimated regression coefficients and the values of the x's. Using our example, we might wish to predict what the value of y would be if x1 equals 2, x2 equals 4, and x3 equals 5. Then we have y hat equals 3.174 plus negative 0.129 times 2 plus 1.478 times 4 plus negative 0.738 times 5. And we would estimate that y would be about 5.13 when the x's have these values.